You want to visit?
Okay, let's start the afternoon session. The speaker is Alexandre.
Zvonkine.
So he'll talk about
This is the third lecture. So before going ahead, I would like to show one application which is kind of outside the scope of Galois theory and surfaces and so on. So there is a question which was asked in 1965. There are two complex polynomials, coprime, and we take the cube of one polynomial and the square of the other one. So a cube, b squared. What could be the minimum degree of their difference? Of the difference of a cube of polynomial and of square of a polynomial. So
why this question? Why this question?
Why this question? Okay, there is 9 minus 8 is equal to 1, and apparently it's the only case when the difference between a cube of an integer and the square of an integer is that small. So the number theorists were interested in the situation how close cubes and squares of integers could be. But having not found another way, they tried for polynomials. Maybe if there are polynomials which are close to each other, a cube of polynomial and a square of polynomial, and we substitute as an x rational number, for example, then probably we get some estimates. This was a motivation, but after that there were already people started to ramificate out of this question. Well, so it is reasonable to consider, of course, a cubed and b squared should be of the same degree. So let us take a of degree 2n and b of degree 3n, so that cube of a and square of b are both of degree 6n, and denote the difference by r. So the four authors, all of them very famous, announced the following two conjectures. First of all, the degree of n is always greater than or equal to n plus 1. n is here, so the degree is 6n. And the second conjecture is that this bound is sharp, that is, one cannot improve this bound. It is the best possible thing to say. To give an example, here is a polynomial of degree 30, degree 10 to cube. Here is a polynomial of degree 30, you see x 15 and squared. So the leading terms disappear quite naturally, x 30 minus x 30, but in fact disappear all terms up to degree 7. The difference is of degree 6. So the degrees 30, 29, 28, 27, and so on, until the degree 7, all vanish, and what remains is only a polynomial of degree 6. Okay, so quite amazing thing. Okay, so the first conjecture was proved the same year by Davenport. So in a way it is considered as an easy one, because the second conjecture remained open for 16 years and was proved only in 1981, and later generalized, and so on. So I will prove the difficult part. I will prove the fact that the bound is always attained for any n, admitting that the degree is always greater than or equal to n plus 1. So in every proof there are two parts. First you must guess something which comes from nowhere, just an insight, and then you go straight forward by some already known ideas. So this is a part that you should guess without any hint. You should divide this difference by r and put 1 to the left and b squared by r to the right. That's all. Now suppose that a cube, that f equal to a cube minus r divided by r is a Belly function. Everything else goes directly through the lines of the theory of descent d'enfant. My question is, if it is a Belly function, what should be the corresponding map? To every Belly function corresponds a map. To every map corresponds a Belly function. What is a map we need for our statement? So, step by step, the numerator of this function is a cube of polynomial. And the polynomial a itself is of degree 2n. Yes. So we need 2n black vertices, all of them of degree 3. Degree 3 because of the cube, 2n because of the degree of the polynomial a. I suppose that a doesn't have multiple roots, so all degrees are indeed 3 and not 6, not 9, and so on. Second step. F minus 1 is a square divided by r. And B is a polynomial of degree 3n. Somewhere it should be written. B is a polynomial of degree 3n. Okay, so my map should have 3n white vertices, all of them of degree 2. If B doesn't have multiples, so I suppose that there are no white vertices of degrees 4 or 6 or something multiple of 2, just all of them are of degree 2. And because they are of degree 2, you may forget them. We may consider a usual map with only black vertices. White vertices just play the role of midpoints of the edges. Okay, so from now on we consider usual maps without black and white structure, just vertices and usual edges. Okay, so black vertices, just vertices, white vertices temporarily disappear from our consideration. So here is the Euler formula. We know that there are 2n vertices, 3n edges from white vertices, and yet unknown number of faces. So we compute the number of faces, which is equal to n plus 2. Now let us take one face and put the corresponding pole to infinity. It will be the outer face. There remain n plus 1 faces, which are finite faces. So our map has n plus 1 finite faces and an outer face. And degree of each root of R is the degree of the face and is the degree of the pole. Okay? So the degree of R is the sum of the degrees of the faces when I take the sum over all the faces except the outer one. And this is the quality I would like to make as small as possible. The number of terms to add is n plus 1. I would like to make this sum as small as possible. So, to summarize, we are looking for a planar map with 2n vertices, all of them of degree 3, with 3n edges, with sum of the degrees of finite faces as small as possible, and the number of these faces is n plus 1. Of course, it is evident that if the degrees of all these finite faces are equal to 1, then we gain. In short, forgot the numbers 2n, 3n, it is just the Euler formula. What we need is planar maps with all their vertices of degree 3 and with all their faces except the outer one of degree 1. Okay, I simulated the problem. I repeat, so I insist on the fact that this is a problem which remained open for 16 years and which was considered by at least 5 very famous mathematicians. I make this psychological attack on you in order to prepare you to what comes next. Solved. That's all, it's the proof. So to construct such a map, you draw first a tree with all inner vertices of degree 3 and then you attach loops to the leaves. And that's all. So just the existence of such maps implies the existence of the corresponding polynomials. Finished the, yes.
Is it easy to compute Penny maps? The Penny maps
to compute this map is incredibly difficult. So the example I gave, this example, you see it was computed 35 years later than the problem was announced. So it is a difficult computation, and it is rather an exceptional case when the coefficients are rational numbers. So for small n, you have some chances to get rational coefficients. For bigger n, it is out of the question. By the way, it is possible to, why I suppose that all my vertices are of degree exactly 3 and not, for example, of degree 6 or 9 or so on. Because of the Euler formula, if I make fewer vertices, I need more faces. So the degree of the difference becomes bigger. Okay, but in return we can get polynomials with rational coefficients. So if we are not so greedy and accept the degree of the difference equal to n+2, for example, we can get more polynomials with rational coefficients. Usually, for bigger n, there are no such polynomials.
So, if I understood correctly, your solution is you take a tree and just you attach groups.
Yes. And the existence of such a map implies the existence of polynomials, but to compute these polynomials is terribly difficult.
So, did the original proof of this bound give polynomials, or did he do something completely different?
Original proof of Stothers, of whom?
So the original proof of the strictness of the bound.
The difficult part.
I don't understand the question, I'm sorry.
So when people first proved the difficult part,
yes.
Did they give explicit constructions or did they do something else?
Well, I don't know, because when I saw the problem, when I read about the problem, I solved it myself in several minutes, and I never looked at the original paper. Not because I'm so clever, just because I was prepared. Okay, so I skip two other funny.
So you skip ABC conjecture. You also have ABC conjecture.
ABC. Okay. Good.
So it's over function field.
Okay. About ABC conjecture. It is not a very serious application, but funny. So I will state the conjecture 3 times with a more and more specific way. So the first statement: if you have 3 positive integers and a plus b is equal to c, then all the 3 numbers cannot have good factorizations and primes. So this is a conjecture which is not stated very appropriately. More precisely, let us consider the factorizations of A, of B, and of C, and take, with all of them are coprime, actually, and we take the product of all primes which are used in these 3 factorizations. Then the statement, more precise than before, but not precise enough, is that this number cannot be too small compared to C, which is the bigger one. finally, the even more rigorous conjecture. If we consider C equal to R to the power of alpha, so alpha is logarithm of C divided by logarithm of R, then for any number strictly positive, strictly bigger than 1, there exists only a finite number of triples such that this alpha is greater than alpha 0. Only a finite number of such instances. One of the corollaries. Let us take A equal to x is on power to the power n, b y n, and c z n, such that this equation takes place. So obviously, if we take the radical r, which is the product of all primes taking part in the factorizations of x, of y, and of z, it will be smaller than xyz, which is smaller than z cubed. So now take the logarithm of c divided by logarithm of r. It is logarithm of zn divided by the logarithm z cubed, which is n over 3. So the conjecture, the IBC conjecture, implies immediately in half a page that all Fermat equations taken together for n bigger than 4, greater than or equal to 4, may have only a finite number of solutions. It is one of the consequences. Okay, if we replace alpha 0 greater than 1 just by 1, the conjecture is no longer true. This is the statement is no longer true. This is an equality, an evident one. So the contribution to R of 1 is 1. The contribution to R of 2 to the power 6n is just 2. Okay, so here we take contribution 1, contribution 2. So what remains is the contribution of this term. And it is divisible by 63, which is divisible by a square, which is 9. So the contribution is not bigger than b over 3. And hence r is smaller than c, so logarithm is bigger than 1. And there are infinitely many such instances. So it is important to take the boundary alpha 0 strictly greater than 1. Okay, so there are some information that maybe this conjecture is already proved. There are a sequence of 4 pages, each of them longer than 4 papers, every one longer than 100 pages, but it is not yet really established that the proof is correct. So before that, people try to look for some triples with alpha, with the parameter alpha as big as possible. And here is the world record, not beaten up to now. It was found many years ago. So alpha is 1.63, more or less. So 2 plus this is 23 to the power of 5. Well, so the idea now is to take a Billy function, to consider this equation. Okay, every term can be positive or negative, so we put them in such a position that there are a sum of 2 positive ones equal to the biggest one. The interest of Billy function is that the polynomials are already quite factorized, because have a good factorization, because there are vertices and faces and so on, with multiplicities which are not so small. So let us take this map. 2 edges if we consider it like as a usual map, or 4 edges if we do not forget about black and white structure. So there is a white vertex here and a white vertex here, both of degree 2. Here is its belly function. F minus 1 has numerator as a square, and we substitute x as a rational number. So we obtain this equality for S and T. We see here already cubes and squares and cubes, so there is some hope to get something interesting. And indeed, for S equal to 23 and T equal to minus 32, we get the second best result. Unfortunately, at the time of taking this research, this number was already known. So the best solution found from this belly function and unknown at the time is with the alpha 1.35, 36. Okay. And at the time, Graham Elkis composed a list of all instances, of all known instances with alpha bigger than 1.2. So using belly functions, people found 700 new instances. Another interesting remark is, by the way, probably it is worth saying that the success is partly due to the fact that here is the factor 64 and t is equal to 32. So there is a big power of 2. Okay. So let us consider t squared minus this polynomial, this quadratic form. It is a square minus something which is a square minus 3 other squares. So if we consider the Pell equation, it has infinitely many solutions, and every third of them has y divisible by 6. We need y divisible by 6. So infinitely often we get this term, this second term, equal to 1. This example, not something similar, but this particular example gave way to some number theoretic estimates made by Carl Wagner. That's all about ABC. Julia said I omit, however. Okay, I must say at least something about Galois action on these children drawings, on maps. So consider an example. Let us consider the tree on the left. One black vertex of degree 3, 2 black vertices of degree 2. So we make, this is a tree, so the belly function, the corresponding belly function is a polynomial, and we can put this polynomial in the form a factor x cubed and some quadratic polynomial to the square. The roots of this polynomial are black vertices. Note that I do not fix the position of the positions of these vertices because they are coupled in a way. I only fix their sum. So there remain one unknown parameter. I will get an algebraic equation with one parameter. It is not very difficult to solve. The condition is that this polynomial minus 1 must have two double roots. Two double roots. Yes. So after solving this equation, I find that A is equal to this one and K is equal to this one, where there is a parameter T, which is plus or minus square root of 21. So if we take one value of the square root, we get one tree. If we take the other value, we get the other tree. These two trees form a Galois orbit. So exchanging plus and minus square root of 21, we exchange trees with each other. So this field is called the modular field of this Galois orbit, and the fundamental fact is that this field cannot be changed. It is impossible to find a solution over the field, for example, q of square root of 5 or square root of 17. Impossible. No other field would work. Okay, so what do these trees have in common? They have in common the degrees of vertices. The same degrees of black vertices, 3, 2, 2. The same degrees of white vertices, 2, 2, 1, 1, 1. And the same degrees of the faces, because there is a single face of degree 7. This is the only information I used in order to write down my equations, my form of polynomials. So the set of degrees is a combinatorial invariant of the Galois action. Now, before discussing the other invariants, I would like to say something, not to develop Galois theory here, but just to explain how it works. So the main question is what can we say about complex numbers if we have at our disposal only algebraic expressions. So we have first of all rational numbers, 4 arithmetic operations, variables to denote complex numbers, logical operations, quantifiers, and the only relation equal. And also because of the negation, we can express not equal. So what can we say and what we cannot say? We can say that x squared is equal to 21. It is possible. Here is the algebraic equation. X squared equal to 21. So x is one of the roots of this equation. But we cannot distinguish between these two roots because there exists an automorphism of the field, of our modular field, q square root of 21, which sends a plus b square root to a minus b square root. And every automorphism of a finite extension of q can be extended to an automorphism of the whole field of algebraic numbers. So everything we can say about a plus b square root, the same thing is true also for a minus b square root. Okay? So if something is true for this number, if some algebraic equation is algebraic expression is true here, it is for this number, it is also true for this number. One of the consequences, it is impossible to express in the algebraic way the predicate x is bigger than x is positive. It is possible to say that x and x1 and x2 are two distinct roots of this equation. We just write x1 squared is equal to 21 and x2 squared is equal to 22 and x1 is not equal to x2. This is possible. Now it is impossible to say that x is real, since any algebraic relation concerning cubic root of 2 remains valid also for two complex cubic roots of 2. But we can say, for example, that a polynomial p has one triple root and two double roots. For example, we consider the set of coefficients of this polynomial. We write down p of x1 equal to 0, first derivative, second derivative is equal to 0, and the third is not equal to 0. For x2, the same thing up to the second derivative, for x3 also, and we end the condition that these three numbers are different, and here is an algebraic equation, algebraic expression, so we must add here this one, and this one, and this one, and this one, and so on. So, more generally, we can say that f is a Belli function corresponding to a given set of degrees. We give a set of degrees, and we can express in this algebraic way that f is a Belli function. Okay, next question. At the time of Galois, the terminology was better than it is now. Galois used two terms, permutation and substitution. Permutation is an ordering of the objects, and substitution is when we substitute some objects instead of the others. So today we say permutations and permutations, but there are permutations in which they count the number of maxima, the number of permutations with forbidden patterns, and so on. And there are other permutations which they multiply and consider the permutation groups, the representation theory, and so on. So these two theories are almost disjoint. Of course, there are some relations, but they are almost disjoint. So it would be better to say still permutation and substitution. So there are three roots, x1, x2, x3, and somebody permuted x1 and x2. Am I able to recognize this fact using only algebraic expressions? So I consider the discriminant, which is the product of the differences between the roots to the square. It is a symmetric polynomial, therefore it can be expressed as a polynomial in coefficients of our polynomial. So, for example, for this polynomial, the discriminant is minus 108. For this one, the discriminant is 49, and 49 is a square. So, for the second polynomial, I can distinguish between this product without squares equal to 7 or equal to minus 7. And if somebody permuted x1 and x2, I can recognize this by stating that this product instead of 7 is now minus 7. But for the first polynomial it is impossible. I won't prove this, but it turns out that this is impossible. So people say that for this polynomial the Galois group is S3, the group of all, symmetric group of all permutations of 3 elements, and for the second polynomial the Galois group is the cyclic group C3. Only cyclic permutations do not permit me to recognize that something happened with the roots. Well, so for example, the symmetry is a Galois invariant. Here are two trees. The first one with the same set of vertex degrees. This one is symmetric, and what does it mean? It means that if I put this point at 0 and take a square of the corresponding polynomial, I get a smaller, 2 times smaller tree. So the polynomial itself is a polynomial in x squared. This is an algebraic condition on the coefficients of this polynomial. So all the coefficients in front of the odd degrees are equal to 0. And the second, for the second tree, this is no longer true. So these two trees belong to different Galois orbits. And since both of them are unique in their orbits, they are both defined over Q, over the field Q. The degree of the extension is equal to the number of elements in the orbit. Here is a very beautiful example. It is related to the, as we see in the picture, it is related to the Davenport-Stothers conjecture. So we have these 4 maps, and we try only by looking at these maps to figure out what is the Galois action on them. So we notice first that this is the only map which has a symmetry of order 3. The others do not have this symmetry, therefore this map may be taken away and it forms a Galois orbit in itself. Therefore, it is divided over Q, so the corresponding Belli function has rational coefficients. This Belli function was found by Brian Birch in 1965 already. It was in their initial paper. Now, the trees B and C are symmetric with the symmetry of order 2 with respect to a white vertex which is invisible here and here. Okay, and if a map is symmetric, okay, so if we put this white vertex to 0, so it is we may apply the same thing. So the Belli functions are functions of x squared. Okay, so these two maps form a separate Galois orbit, and it is also obvious geometrically that the corresponding field is quadratic imaginary field, because the complex conjugation sends one map to the other one. Finally, there is one map which remains, which doesn't have any particular characteristics, but which is defined over Q, over rational numbers, just because it remains alone, without any reason which would be special for this map. All the reasons are special, all special reasons are concern other maps, but this map remains alone in its orbit, therefore it is defined over Q. And it is the example I showed of the polynomials of degree 30, with the difference being on degree 3, corresponds to this map. So our theory, the theory of Dessins d'Enfant, doesn't make the computation any easier. What information it gives is that without any computation, I can tell that there are exactly 4 non-equivalent solutions to this problem. For n equal 5, exactly 4. And there are 2 of them defined over rational numbers, so the polynomials, the rational functions with coefficients in Q. And one of these two cases, in one of these two cases, we have polynomials which are polynomials in x cubed. In the other case, it is just some polynomials. So it is maybe 35 years which took to from the computation of this example to the computation of this example, they may be due to the fact that nobody guessed, nobody knew in advance that that there is one more solution over rational numbers. Okay. So a symmetry is a composition, as I already said, not explicitly. A symmetry, for example, of order 3 means that the corresponding function is a composition of some function of smaller degree, and we substitute x cubed to this function. So it is a composition of function with a polynomial x cubed. Here there is a more complicated composition. We take first the polynomial corresponding to this tree, and then insert this polynomial into a Billy function corresponding to this map. So instead of taking the pre-image of the segment 0, 1, we take the pre-image of this map, which is of degree 4. What we get is this result. If we fix, so there is no symmetry here. If we fix the set of degrees, there are many maps like that. For example, these petals can be taken all three here, and something else. These two petals can be put below or above. So there are many maps with the same characteristic, with the same symmetry, and with the same set of degrees. But this one is defined over rational numbers because by construction. Because the Billy function here is defined over Q, and the polynomial here is defined over Q. And the fact that a map is a composition, that a Billy function is a composition of Billy functions of smaller degrees, can be also expressed in terms of cartographic groups. The cartographic group of such maps are imprimitive. So there is a way to detect a composition by considering groups. And maybe I stop here because the next example is very beautiful, but needs some time. So an automorphism group is a Galois invariant. This is that's obvious. Okay, so I stop here.
Any question? Comments from Norbert?
Yeah, any pictures or 2 pictures or
No, they are handmade.
Word by the next example.
Next example.
Yeah.
No, this one. A family of maps with the degrees of black vertices 5, 5, 1, 1, white vertices all of degree 2, and and faces of degrees 5, 5, 1, 1. So there is an extremely interesting Galois theory which can be detected only by looking at these pictures. So what is written here, we are in a desert and have only a little stick to draw on the sand. What can we say about the Galois action, about the action of Galois group on this set of maps? And we can say quite a lot. not everything. For example, we cannot compute the fields in question, we cannot compute the groups in question, but many things can be said only by looking at pictures.
So, in the, I guess the second last example, where there's 4 different maps, and you deduced that 2 of them are in the same, they form a separate group.
Yes.
So, you can show this only by doing computation, or it follows from general fields?
For imaginary fields, it's more or less obvious because there is a complex conjugation, which is the only element explicitly known of the whole Galois group. Okay, so if we make the complex conjugate complex conjugation and get the other map, it is more or less obvious that there is the field is quadratic imaginary. But when the field is quadratic and real, we cannot say it by just looking at the picture. Because it might be a quadratic real field or just 2 separate orbits defined over Q.
Can you find orbits, situations where all possibilities of realizing your vertices is one orbit? So
No.
not the easiest, not the AN.
I see. It seems that I don't have such an example. It seems. Well, maybe yes, but I will look. I will look at.
Our question is, can you make with pictures, given a finite group, a polynomial having that group as Galois group?
As a cartographic group, or is
So
it?
you have a finite group,
No.
and you wish to realize it as Galois group.
So you state the inverse Galois problem. Yes, I can. But I will not disclose it. Yes, we can.
Okay, I think the next topic we started soon, so let's thank speaker again. Hugo, I think you are starting now. Right?